Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing a very important topic in the last lecture, and this is about transition metal carbonyl, its bonding properties. In transition metal carbonyl bonding properties that we have been studying, what we saw is that in order to understand metal carbonyl transition metal carbonyl bond, we need to first understand carbon CO bond or carbon monoxide bond, and this to understand this we have treated this metal carbonyl interaction with regard to molecular orbital theory, particularly constructing the molecular orbitals of carbon monoxide, and this we have done by looking at how the atomic orbital of carbon and atomic orbital of oxygen combine to give the carbon monoxide molecular orbital. Now, having done this construction of molecular orbital in the previous lecture, what we had discussed upon is frontier molecular orbitals of the carbon monoxide which interact with the frontier atomic orbitals of the metal. And what we had seen that frontier molecular orbitals of the carbon monoxide consist of sigma orbital on carbon which contains the lone pair, and that can be given as something like this. And it has the lone pair. So, this is S sigma star or 5 sigma orbital. So, this is a field orbital which is sort of the HOMO of carbon monoxide, and we had also seen the LUMO contains two degenerate orbitals which is a p type and contains the interaction like this. So, this is a pi star orbital, and similarly there can be a CO pi orbital corresponding to that. Similarly, a pi orbital which is CO pi now. This what is interest, what we are right now focusing on this lecture is this, how these orbitals, one sigma and one pi orbital CO pi and CO pi star, these orbitals, how does it interact with the metal orbitals. So, for example, as for the CO sigma star which interacting containing a lone pair interacting with the metal orbital, the interaction is so this is empty and this is filled, and this is often referred to as metal sigma CO2 metal sigma or this is called sigma donor interaction. Where the interaction is happening over here. Now, the other important interaction which will happen is that this empty pi star will interact with filled metal orbital as shown over here, and this is called metal pi to CO 2 pi or pi acceptor back bonding. Interaction. Now, apart from these two interactions, this one and this one which has been discussed here, there is another interaction which is often neglected, but nonetheless I would like to show it in this discussion, is that this CO pi orbital donating electron to metal pi orbital which is empty, and this is filled, and this is called CO 1 pi to m pi donor bonding interaction. But this interaction, pi donor bonding interaction, which is depicted over here, is often neglected. Mainly when people talk about metal CO interaction, they talk about the two interactions. One is this CO to metal sigma interaction, and the other is metal to CO pi back interaction. These two interactions are often spoken about, and this interaction of CO filled to metal pi vacant is often neglected, but nonetheless this is an important interaction and is being discussed in this current topic. Now, what is important that each of these interaction affects the metal CO bond order, also bond order of CO and stretch new CO stretching frequency. So, as this forward sigma donation or backward pi donation, forward pi donation affect, then it affects the metal CO bond order as well as CO bond order, and as a result the CO stretching frequency increases or decreases, they get affected. Now, what has been observed is that as the metal C bond order increases because of sigma donation of the carbonyl, if this sigma donation increases, then metal C bond order increases. Similarly, if this interaction, this donation pi to the metal vacant increases, then again the metal C bond order increases, because now a bond is being formed, and if the metal to pi back bonding interaction also increases, that also leads to increase in metal C bond order. So, what we see is that the interaction between CO and transition metal in forward sigma donation, forward pi donation or backward pi donation increases the bond order of metal C. However, the forward sigma donation, forward pi donation, backward pi donation affects the CO bond order differently. For example, in the forward sigma donation, metal CO sigma donation, the CO bond order also increases, and that is because when the electron density is moved from carbon onto the bonding region, carbon develop positively charged, and that the CO bond now is more tightly held. As a result, the CO bond order increases and stretching frequency of CO also increases. However, when the CO to metal forward pi donation increases, then the CO pi bond weakens because of this pi donation, and as a result CO bond order decreases. And if because of the pi electron now being donated to the metal, CO bond order decreases, then CO stretching frequency also decreases. And lastly, when metal to CO pi back bonding increases, there too, since the electron is being dumped on the anti-bonding orbital, so the CO bond order again decreases, and correspondingly CO stretching frequency decreases. Now, what we come to see is that this CO stretching frequency is an important experimental marker that can reflect on this three interaction, this one forward sigma donation, forward pi donation as well as backward pi donation. And from the increase or decrease or variation of the CO stretching frequency, one can have an insight into the extent of forward donation that CO is undergoing with the metal orbital, or the extent of backward donation that the metal orbital is undergoing with CO. Now, as I said in the beginning of the discussion that the forward sigma donation and backward pi donation are the ones which are mostly spoken about, and this forward pi donation, the one that is shown over here, is less prominent or more often neglected, but these are more important when it comes to sigma pi kind of bridging modes, where the pi orbital gets engaged with a metal pi type empty orbital and donates its pi electron cloud onto the metal pi vacant pi orbital. As a result, since the electron density of the bonding pi orbital is given to the vacant metal d orbital of appropriate symmetry, the pi bond weakens, and as the pi bond weakens, the CO bond order decreases and CO stretching frequency decreases. Now, as for the metal to carbon pi star pi back donation, the electron donates onto the pi star orbital. Now, if pi star orbital gets strengthened, that means the CO bond order decreases, and as a result the CO stretching frequency decreases. So, this is a very important slide which gives a total perspective of on how CO interacts with the metal and how this interaction may affect CO stretching frequencies. We are going to deal these in more details. For example, we are going to take a look at series of complexes. These are all D6 type complexes For example, between hafnium CO6 2 minus, this is a metallate, this has D6 electron. Then let us say tantalum CO6 minus comes tungsten CO6, which is a neutral, then comes rhenium CO6 plus, followed by osmium CO6 2 plus, finally iridium CO6 3 plus. All of these are D6 systems, that means it has D6 systems, but it goes from anionic electron rich metal center to cationic electron deficient metal center. As a result, the backward pi donation decreases or sigma interaction increases this way. So, for this kind of complexes, so more on the right hand side, the less is the back donation and more is the sigma interaction, and on going from right to the left, increasing the left one being more electron rich, it undergoes increasing pi acceptor interaction or pi back bonding interaction. So, on one side, on the left hand side, we have anionic electron rich complexes, on the right hand side we have cationic electron deficient complexes which will not undergo pi back donation. The ones which it will not undergo pi back donation, for them the nu CO stretching frequency will be the highest, and that is exactly what we see centimeter onwards. For example, for hafnium, which is highly electron rich, can undergo significant amount of hafnium CO back bonding, has very low stretching frequency of 1757. Then tantalum, which is slightly lesser electron rich, has 1850, tungsten 1977, rhenium 2085, osmium 2190, and iridium 2254. So, this is a nice example where the metal ligand, metal CO sigma as well as metal CO pi back interactions that we have studied, how they can be explained. They can be used to explain the variation of nu CO stretching on going from very electron rich metal center to a very electron deficient metal center. And what it is observed, that the more electron deficient metal center cannot undergo pi back donation. As a result, the CO stretching frequency is the maximum, and a electron rich metal center which can undergo pi back donation will lead to weakening of the CO bond order, and that would be followed by lowering of CO stretching frequency. We will take a look at few more, or the type of binding modes of CO and how that correlates with the CO stretching frequencies. That will also give us insight as to how the binding modes affect the metal carbonyl stretching frequency. For example, for free CO, the new CO stretch is 2143. For terminal CO, new CO stretch has reduced. Now, as opposed to free CO, the metal can undergo pi back donation to the extent of its electron richness, and one can observe a range where it has gone down to 1850, where significant amount of back donation has happened, to 2120, which is very high and close to 2143, where minimal amount of back donation has happened, to mu 2 CO, where CO can bridge between two metal. Now, bridging COs, there is significant amount of interaction or back donation from the metal, and the bond order right now has moved from 3 to 2, and that is reflected in the CO stretching frequency, where it has even further fallen to 1750 to 1850 to something like mu 3 CO, where now CO is bridging between 3 metal centers, and for that this has also fallen substantially from 1620 to 1730. So, what we see is that there is a huge amount of correlation happening between the binding modes of CO and the corresponding stretching frequencies, and what one sees is that if one goes from free carbonyl on the way to terminal metal carbonyl, where carbonyl is bound to 1 metal, to the mu 2 bridging type, where carbonyl is bound to 2 metals, to mu 3 bridging type, where carbonyl is bound to 3 metals. In all of the cases, the stretching frequency decreases on going from 2143 to 1850 to 2120 to 1750 to 1850 to 1620 to 1730. Now, electron density of the metal, which is reflected or ascribed by the charge on the metal, leads to variation in electron density, and that can be seen for these following kind of complexes. These are all D10 complexes. Let us say nickel tetracarbonyl, which has a nu CO of 2060. Now, when it becomes to cobalt tetracarbonyl, this is also a D10 system. Now, this being monoanionic, so metal is more electron rich, and now the nu CO has further decreased because of extensive back bond donation to 1890, then to iron tetracarbonyl for 2 minus, which again is a D10 system. Now, it is dianionic, it even goes further to 1790. So, what we see is as the metal center is more electron rich, then the metal to CO pi star back donation increases. As a result, the CO stretching frequency decreases. The same is observed in another set of D6 systems. For example, MnCO 6 plus, which is a D6 system. Now, this being a cationic complex has cannot undergo too much of back donation, and hence now the CO stretching frequency is quite high, because there is very little back donation happening from cationic manganese onto the CO pi star, as a result leading to very high CO stretching frequency. Then another chromium CO6, this is the neutral D6 compound, where relative to manganese cationic compound significant amount of back donation happens, and now 2090 has reduced to 2000 centimeter inverse to finally going to anionic VCO6 minus, where metal is more electron rich, back donation is permitted, and then this has even gone further to 1860. So, just to give you a feel, for free CO where there is no back donation occurring, the stretching frequency is very high because of the triple bonded nature of the CO bond, and that arrives at 2143. So, with this, let me summarize the development which has been spoken about in today's lecture. We have looked at various kinds of binding modes of carbonyls to begin with metals, and what we saw that the interaction of the frontier atomic orbital of the metal plays a key role in understanding the metal carbonyl binding, and that can happen through sigma donation from the carbon lone pair onto empty metal orbital, or the pi orbital of the CO donating onto the empty metal orbital. This is pi forward donation. This usually is kind of neglected or not so common, and the last kind of interaction that may happen is from filled metal orbital onto vacant CO pi star orbital. Now, we had seen that how each of these interaction would affect the CO and metal carbon bond orders, and which can be reflected in the CO stretching frequencies. On that in mind, we have taken a look at some of the examples where we saw that variation of metal electron richness of the metal for a particular valence orbital, let us say for D6 or D10 systems that we have looked at, that we saw that as one goes from electron rich to electron deficient metal center, we see that with the decrease in the back donation, the CO stretching frequency increases for electron deficient metal center. So, we have also discussed about the correlation of types of bridging with regard to terminal or mu 2 CO or mu 3 CO of carbonyl with the metal center with respect to how they affect the stretching frequencies of the CO bond. So, with that, let me conclude today's lecture, where we have given a brief as well as very detailed discussion on how the CO stretching frequencies can be actively used in understanding the type of interaction that may happen between those frontier orbitals of CO with that of the frontier atomic orbitals of the metal, and how these interaction will help detect or determine the kind of stretching frequencies or variation in stretching frequencies that one observed. So, with that, I would like to thank you for being with me in this lecture, and I am going to take up more detailed reactivity studies and other properties of metal carbonyl complexes, which are crucial to understanding this important class of compounds in the next lecture. Till that time, goodbye, and I look forward to being with you in the subsequent lecture. Thank you.